Hey guys, this is Siri and I'm back with another PyTorch video, and in this video we're going to be introducing PyTorch's automatic differentiation engine, AutoGrad, and we'll see what that means in a moment. Let's first just do a quick recap of what we've been discussing over the past 4 or 5 videos. So we've been discussing this whole learning process, this whole machine learning process, training process, what that even means. So hopefully now you have a better idea of what this whole process is all about and what we're trying to do, what the end goal is. So we're trying to, have inputs be paired with outputs and, find the best way to model that data. We did a linear mathematical model example, so we didn't really bring in that non-linearity just yet. We did some definitions here, model definitions, loss function definitions, parameters, what a loss function is, what parameters are. So before jumping to this video, I would make sure that you know what these are. And I've covered them in my previous videos, so feel free to check them out. But it's like you kind of need these in order to, get a full understanding of what AutoGrad actually does. So we also talked about how to update those parameters. We've talked about, testing and like the sort of trial and error, but it's not really trial and error because we're making educated guesses using the rate of change of the loss. And, we do this chain rule and we take the derivatives. We've seen how derivatives actually play an important role in this whole machine learning process because it helps us find the right parameters, the right slope, and the y-intercept, the w and the b, that actually model our data and represent our data, right? Because if we have 4x plus 3, that might better represent our data than x plus 2. So we need to find the perfect w and the perfect b, and we do that by looking at the loss function, taking the derivative of the loss with respect to the parameters, and updating it based on that. Okay, so we've defined a gradient function, which is a gradient is just a vector of derivatives of the loss function with respect to each of the parameters. We've talked about the learning rate as an extremely important hyperparameter, and we've talked about how normalizing inputs might be a good idea to prevent overshooting and overcorrecting of your parameters. And we've defined this whole training loop, we've made use of all our functions, and now we're here, okay, to talk about PyTorch's automatic differentiation engine. Okay, so PyTorch automatic differentiation engine. So what does that even mean? What on earth does this mean? Well, you might recognize the word differentiation if you've understood what we've been talking about, because differentiation just means, taking the derivative, right? So we've come a long way just by, taking a few derivatives here and there using the chain rule. And so if we have more than 2 parameters, and if we have a more, or like a deeper network, and we'll see what that means in a few videos, right? What I mean is, like, if we have some more, if it's not just a linear relationship, if we have more relationships, if it's not just like a bivariate sort of, relationship between the input and the output, and we have more things going on, it's going to be harder and harder to take the derivative of each one of those parameters, because now you're not only dealing with the y-intercept and the slope, you're dealing with much more complicated things. And so it's going to be hard, it's not going to be easy, it's not going to be interesting, it's not going to be fun, it's going to be tiresome, and it's going to be, most of all, like really, really hard, okay, to take the derivative of the loss with respect to each of the parameters, because first of all, we don't even know. We can have like millions of parameters, okay, if we're dealing with a neural network that has both linear components and nonlinear components. And so we need someone to help us, and we need something that can, take these derivatives, right? We don't want to sit here, you know, let's just take a look at what we did here. You know, we literally did the chain rule ourselves. You know, here, right? d loss dTp, which was the temperature predicted, you know, dW, like you see dy, dx, taking the derivative with respect to x and with respect to these things, these like parameters, right? We literally did the chain rule here, like ourselves. We manually wrote it ourselves, but that's not practical or realistic when dealing with millions of parameters. And so that someone who's there to help us is PyTorch, okay? And we have PyTorch's automatic differentiation engine. Other deep learning frameworks also have automatic differentiation engines. But I think PyTorch's one is more like, it's easier to understand when you're first learning about it, I think. So the name for PyTorch's automatic differentiation engine is AutoGrad. Okay, and I guess you can kind of see here, right, like automatic, auto, and then grad is for like gradient, right? So, you know, we've talked a lot about tensor operations in our, you know, if we go way back to before this whole learning process sort of thing. We've talked about like the basics and the bare bones of tensors and what we can do with them. We've talked about operations, but we didn't talk about everything in tensors, about tensors. Okay, and the thing that we didn't talk about is how tensors can keep track of like how they came to be. So what do I mean by that? Well, we update parameters, right? And parameters are tensors. And when we update them iteratively, we have this sort of like train of values that it once was. Like it starts out here and then we apply some operations and to update them, to make it better, to make it better, to make it better. And then you have this whole like tree that you can track and this whole history that you can track of how this tensor came to be. Now, why is that useful? Well, if we want to take the derivative of the loss, which is the output, with respect to its parameter, then we need the chain rule, as we've mentioned and discussed before. And that means that we need to know the functions, or in other words, the operations that led up to this this final tensor, so that we can, you know, take the derivative and go back and go back and go back and go back. So there are two passes. We call these sorts of things two different passes. And these two different passes are first the forward pass and the backwards pass. Okay, so the forward pass is, you know, the things that we've been doing. We, you know, like, I mean, it'll make more sense when we talk about combining different sorts of components, like a linear component, like what we're doing here, with other linear components or other nonlinear components, and we put them together. So we have like different sections, like we've talked about at the very beginning of our neural network, which is just this web, this mathematical web. It's nothing different than what we've been doing here, except there are just more functions. So we have sections, like a linear section and a nonlinear section, and we call these different layers. And the input of one layer is going to be the output of one layer is going to be the input of the next, and the output of this one is going to be the input of the next, and so on and so forth. And that is what we call the forward pass, because we're applying these series of computations, both linear and nonlinear, so that we can just decipher a pattern between, like a pattern that is occurring, and the relationship between the input and the output through these computations. That's the forward pass. But along the way, you need to take the loss, right? We need to find the loss, and we need to update the parameters, right? The W and the B along the way in each of these layers, and maybe multiple times in each layer, right? So we also need the derivatives. So we move forward, and then we need to go back again as a part of the chain rule and say, hey, how did we even get here? Well, we got here by applying this operation. How do we get here? By applying this operation, by applying this operation. And so this is, PyTorch can track that, and it can give you the gradients of each parameter, the derivatives of the loss with respect to the parameters in the backwards pass. So in the backwards pass, we compute the gradient. Okay, the gradient is a vector of derivatives. And, so PyTorch also, along with doing this, it creates a graph, a computational graph. And so what does it have in this computational graph? Well, it has the W and the B that we start out with. It has some intermediate steps. Okay, some more intermediate steps. Some more. And then we get to our y, in our y equals mx plus b. Okay, this is probably the first iteration. Hey, this is how I'm updating my parameter. I want to say that instead of like 1 and 0, it's like 4 and 2. That's my first round. This also might be pretty wrong, but it's a lot better than this. So, we have some W and B, we have some intermediate steps, and we have a Y. And we call this W and B a leaf node. We call both of them leaf nodes. Okay? This whole computational flow of starting off with some initial parameters and updating them through some intermediate steps and the loss function and whatnot, and getting to the Y, none of it would be possible without the W and the B. Because even though you might, create new tensors along the way, right? We create new tensors along the way, right? These were based off of W and B, right? So this is literally where the computation begins. Okay, so this is where the computation begins. And so these are are non-leaf nodes, and each operation we call a node. Okay. And and the result of each new computation will be along the way, right? Will be at each node. And so I guess this would be more clear with a sort of picture or something. So maybe I might add one in the description, but I can, make some stuff up, really. Actually, no, let's do that later. But you can sort of imagine this sort of graph, and, we have a flow chart of what all our computations are, and we have some W and B starting out here, and there are, some computations. These are nodes, and then we have a new tensor, and then we, do another computation, and then another tensor, and then another computation, and then another tensor, and all these intermediate tensors, okay, we need to make sure that, PyTorch is still tracking these gradients. So how do we make sure, now that we know how it's doing this, right? Now that we know about a computational graph, we know about the backwards pass, and we know that we need the chain rule to compute these gradients, and we know that PyTorch is going to help us. now we can ask ourselves the question, how is PyTorch going to help us? What do we need to do? Okay, and what we need to do is, well, first let's copy paste our model definition and our loss definition so it's easier to see. So we're not going to be using this anymore. We're not going to be, manually writing down, oh, the rate of change of the loss with respect to this parameter is this. No, we're not going to do that. I mean, like the actual model definition up top here. So just the linear sort of thing. Okay, and the loss. Okay. And is there anything else? Yeah, the initialization. Okay, and we should note that no matter how nested your forward pass is, no matter how complicated, and no matter how many computations there are in the forward pass, PyTorch can go back. It can, no matter how much we go forward and like to get to our output, or at least the output that we think it is at the moment, PyTorch can keep track of this and go back and go back and go back and go back, no matter how much stuff there is in between. Okay, so okay, we just initialized our parameters, and I want to initialize our parameters in a different way. Okay, and we'll see how. Okay, we used params in our in a couple of function definitions above, so that shouldn't be new to you. These are just our weight and bias. And let's say that it's torch.tensor. We're initializing our weight as 1 and our bias as 0. So it's 1.0, comma 0.0. And requires grad is equal to true. Okay, this is an attribute that I am, defining here. Not defining, I mean like setting. This is an argument, a keyword argument that I am setting equal to true. Okay, and so what does this do? What am I doing here? Well, saying that requires grad is equal to true is telling PyTorch that you want to require grad. And what that means is that you're telling PyTorch, hey, I want you to be able to keep track of the entire thing. It doesn't do that automatically. We need to specify that. Okay, requires grad is equal to true. So now we have this whole tracking of tensors. So the intermediate tensors, if we need the chain rule to get to these intermediate steps, right? So we need to be able to apply the chain rule on all of these, which means that if we want to do it for this one, we need the info of all these, right? All these below it. So these were like ancestors of W and B. These come from W and B. And if W and B have their requires grad attribute set equal to true, then anything that results from W and B, literally all these non-leaf nodes that result from W and B that help you get to this y equals mx plus b, can track their previous steps and compute their gradients using the chain rule. Okay, so if the input tensor has requires grad set equal to true, then their output will too, and vice versa. If it's set equal to false, then we can't take the gradients of the loss function with respect to W and B because we don't have access to all of these yet. Okay, and the nodes, the gradients only get populated at the leaf nodes, so all these intermediate steps, in order to save at least the primary reason is to save memory. and that's why we don't, populate the attribute, or like the gradients for these ones. Okay, so, but it doesn't have, but the W and B do have information from these, obviously, right? Okay, so now the value of the grad attribute is going to be equal to the derivatives now once we call this function, a specific function, which is backwards. Okay, so first we didn't call backwards yet. We didn't tell PyTorch to make the backward pass yet. Okay, what we're saying is once we do what we're asking here is like PyTorch, when we do this backwards pass, be sure to track the history so that we can use the chain rule and go back, okay, to compute the gradients, because that's how we update our parameters, right? We need that information because it's very valuable and it's going to help us make the right decisions and the right updates to our parameters so that it models our data best. Okay, so params.grad, okay, this is the grad attribute. Okay, this is the requires grad. These are different. Grad attribute. Okay, and it'll be none. Is this none? Okay, we didn't run this yet, and I'm afraid that, okay, never mind. Okay, it's true. Cool. So most of these functions, most of these operations that we perform are going to be differentiable, so we can take the derivative. Okay, and if that's not familiar to you, like if this whole idea doesn't sit well with you, I would definitely recommend, watching a couple of videos or reading on the idea of differentiability and, derivatives and just like the introductory material. You don't really need to go too much in depth of like an entire calculus course, although it would be helpful if you had the time and interest, but you do need to know the introductory stuff. So yeah, let's define the loss now. Let's say that loss is equal to the loss fn, the function that we defined above, and let's call it with the input as our model prediction, right? So now params tc, this is just like star args, right, if you're familiar with that. So it's a variable length arguments. Okay, and let's call backward. Okay, this is a function. Okay, when we call backward, okay, PyTorch is going to make that backward pass. Okay, like on this computation graph that we've talked about above here, right? So let's run it. TC is not defined. Oh. Okay. Okay, wonderful. And so now let's take a look at params.grad. Okay, this is a Boolean value. This will store the derivatives, the vector of derivatives, which is the gradient. Okay, this is why they're different. I'm talking about params.grad right now. Okay, so let's see. Okay, so what do we have here? We have two values for our derivatives of the loss with respect to W and with respect to B. Okay, so it's kind of nice to see how, we actually have these values and we can see them. And I hope this makes this entire process of taking the derivatives via chain rule, I hope that makes it more transparent now, and now that we can see what's actually going on. And yeah, I think that's it for today. We'll talk about the problems you might encounter when dealing with AutoGrad, and about the accumulation of gradients, which is not good. So we'll talk about that in our next video, but I hope you learned something new today, and I hope you appreciate AutoGrad more now that we've already, went through, defining like this whole chain rule process ourselves. Usually if you just if you just learn about AutoGrad, you're like, okay, yeah, cool. But now that you know the process for doing it like by hand, and now that you can hopefully imagine what it's going to be like to do it for like a million parameters, or at least like 100 or 200, it's going to be hard. And hopefully you now appreciate AutoGrad more now that you know about that. Okay, so I think that's it for this video. I hope you learned something new today, and don't forget to like, comment, and subscribe.